helps if I plug this in.
So I just wanted to point out, while I'm thinking of it, because I'm not sure if I ever pointed this out, and you might find it helpful. If you go on our class webpage, of course there's a calendar and you can find, links to recordings of lectures and stuff like that. But also, did you know, right here it says lecture notes. And if you click here, this is a big PDF with all the lecture notes that I've written up for this class. So, I wrote them up when I was teaching it in a previous semester. So, this may not always correspond, like if you look at the dates, I'm not sure the dates always correspond exactly when we talked about that thing. And there's going to be a few differences, like some of the stuff I'm going to tell you about disco may not be written in here, but whatever. The point is, much of what we talk about in class is written in here. So that's just another resource for you, especially if you're like, oh, there was that one thing we talked about, on that topic, and you don't want to go and find which video it was, and find the place in the video where I talk about that. You can just go through this PDF. Anyway, just wanted to mention that. You don't have to look at them, but is available. All right. So, we're going to keep talking about sets today. So last time we defined sets, and well, actually we didn't define them last time. So we talked about a bunch of operations, some operations we can do like Cartesian product. We talked about power set. I guess we finished talking about empty set stuff. Okay. So today we're going to see some more operations we can do on sets. So operations. So the first thing we're going to see today is intersection. And I'm going to define it like this. Definition. The intersection of sets A and B is, well, it's basically like where they overlap, right? So it's the set of elements common to both A and B. So that's kind of the way to define it in English. We can define it using sort of formal logic or formal notation like this. And here's how we write intersection. We write it like this kind of upside down U. That means intersection. So it's the set of all x such that x is an element of A and x is an element of B. Okay, and we could also, another way we could think about it is we could think about it graphically. So if this is my set A, so A is kind of like, all the stuff contained inside this circle is like my set A. And here's the set B. Right, their intersection is this part here. So this is A intersection. And maybe you've seen Venn diagrams before, right? So this is what's going on. So any questions? So this is a Venn diagram. I'm guessing some of you have seen Venn diagrams before. If you haven't, that's okay. It's a way of kind of visualizing different sets and their relationships by by, drawing circles, or it doesn't have to be circles, some kind of area to represent each set, and then you can see kind of where they overlap or where they don't overlap. So we'll definitely use these to reason informally about things, although, yeah, they're often a good way to visualize what's going on. And, as an example, if I have, like, for example, a set, 1, 2, 4, 5, 7, if I find the intersection with, 1, 3, 4, 8, well, it's just which elements are common to both. It looks like 1 is in both of those, 4 is in both of those, and I think that's it, right? So that would be the intersection of those sets. As another example, I don't know, let's see. Let's do something with some infinite sets. That'll be fun. If I say the intersection of the natural numbers intersection with x such that x is an integer and x is less than 5. So, okay, this set is, 0, 1, 2, 3, 4, 5, 1 to infinity. This set, it's all the integers that are less than 5. So remember, that includes negative numbers, right? So this is like, well, it has 4 in it, and 3 and 2, and also negative 20 and negative 1,000. But the intersection, right, what numbers are in both of those? Well, it's just 0, 1, 2, 3, 4, right? So you'll see, this example shows the intersection of two infinite sets could be finite. It could also be infinite. Can anyone think of an example of two infinite sets that have an infinite intersection?
So this isn't exactly like, what would happen if you changed it to all, like, x is greater than 5, so it's all integers greater than 5?
Good. Yeah. Good. That's a good example, right. So, if Grace is saying, well, if I just change this less than to a greater than, that works, right? Because all integers greater than 5, that's like 6, 7, 8 on forever. Right, and then if I intersect that with the natural numbers, actually I just get like the same thing as this, is their intersection. Because everything in here, like this is actually a subset of the natural numbers. And so, yeah, that would be a good example. Right. Cool. So, union, definition. The union of two sets A and B is a set of all elements contained in either one. Right, that is A union B. So for union we use, it's the same symbol but flipped upside down, or flipped right side up. Sure, everybody knows that. It's like a little U. notice how similar that is to intersection, right? But we have an or instead of an and. And lucky for us, the symbols are the same way around. So like, this U corresponds to this kind of the or symbol, right? And the intersection is pointing up just like the and symbol. That's not a coincidence. So we can visualize it like this. Right, here's A, here's B. Their intersection is everything, right? All of this, that's all their union. Oh, sorry, did I say intersection? I meant their union. Their union is all of them. Right, so, you know, for example, let's do this the same. 2, 4, 5, 7. Union, 1, 3, 4, 8. Right, I just take every element that's in either one. But because these are sets, I don't care whether I have 2 copies of something or 1 copy. So it doesn't really matter, right? It's just like, is it in one or both? I don't care. So 1 is definitely in there, 2, 3, 4, 5, 7, 8. And if I union these 2 sets, what do I get if I union the natural numbers and the set of all integers that are less than 5? What was that?
Do you get natural numbers?
Natural numbers. I think I get more than just the natural numbers. So remember, the natural numbers start at 0 and go up. They don't include negative numbers, right? But this is all the integers that are less than 5, so that doesn't include negative numbers. JC?
So it should be from negative infinity to 4.
Negative infinity to 4? No. Garrett?
It would be from negative infinity to 0, and the 0 order with all natural numbers.
Yeah, so is there a nice name for what that set is? Yeah.
Set of integers?
Yeah, it's just a set of all integers, right? Every positive or negative integer is in there at least once. Right, so the numbers between, 0 to 4 are kind of in there for multiple reasons, but it doesn't matter how many reasons you have for being in there. You're either in there or not, so. Okay. Here's a question for you. What can you say? What can we say? And there's multiple answers to this. I'm curious to hear what you think. What can we say about the size of A union B? Anything interesting you can say about the size of A union B? Size meaning the number of elements. And we're just talking about finite sets now, right? So don't worry about this example. Maybe just think about this example. Mason?
Size will be greater than or equal to the size of the bigger set.
Okay, so you're saying the size of A union B will be greater than or equal to the size of whichever one is bigger. Maybe I could say like max of the size of A and the size of B. That. You all agree? Okay. Yeah, this makes sense, right? Because, I mean, everything, at least it's got to have, let's say A is bigger. Well, everything in A has to be in here. There might be some extra stuff too, but it's definitely got to be at least that big. Could this ever be equal? In what cases would this be actually equal and not greater?
If the smaller set was a subset.
Right. If B was actually a subset of A, unioning it doesn't really change anything, because those are already all in there anyway, so. In that case, A union B would actually be equal to A, so they would have the same sign, yeah. But definitely, I agree, this is, okay. Anything else we can say about it? Like, I don't know, maybe can I put, period of equals, can I put like something over here? I say it's less than equal to something? Like bound it in between, like, this is the worst, kind of the best case and the worst case scenario?
It'll be less than or equal to the size of A plus the size of B.
Yeah, good, so. That makes sense, right? And when, Olivia, when would it actually be equal?
If A and B are like two different ones.
Yeah, if A and B are like totally separate, they don't have any overlap at all, right? Then the union will just be like, well, literally you take everything A and also everything in B, and they're just all separate, so the size is just the sum of those things. But if A and B have any overlap, right, then it's not going to be equal, because you kind of don't count those things to overlap twice, right? Okay. So good, very good. And can I actually, there's something else that we can say about it, and maybe inspired by our discussion about, you know, like it's equal to this, it's equal to A plus B if there's no overlap. But if there is some overlap, it's going to be smaller, right? Can we say, can we give some kind of formula to say, like, how would I actually compute the exact size of this? Like, can I say what it's equal to in terms of other things? I mean, it's equal to itself, I guess. But. Any ideas? Or let me give you a hint, kind of what I'm getting at. What I'm trying to get at is, I want to say something like this. So we had a rule like this for Cartesian product, right? If I do the Cartesian product of A and B, the size of that is exactly the size of A times the size of B, right? That's really nice. I want a rule kind of like that for union. I want to say the size of the union of A and B is the size of A plus the size of B, except that's not quite right. Right? That would only be true if they are completely separate. So how can I fix this? Yeah, JC.
Is it same as my intersection?
Exactly. Minus the size of the intersection. Right? Why is that? Well, if I look up here, if I add these, if I add, you know, the size of A plus the size of B, then I'm going to count, whoops, oh no. I'm going to count this area twice, right? Because I counted it once when it was part of A and once when it was part of B. And I don't want to count it twice, I only want to count it once. So if I just subtract it once, now I've only counted it once. And we can look at, like in this example, right? So here, this has a size of 5. This has a size of 4, and by add them I get 9. But their intersection, I think, had two things in it, right? 1 and 4. If I subtract that, I get 7, which is the size of their. So this is called the principle of inclusion, exclusion, or important principle, and we'll talk about this more later when we talk about more about consequences. So this is like a super simple baby version of the principle of inclusion exclusion. The real principle of inclusion exclusion actually is much more general than this. It talks about like more than just two sets and whatever. But this is the basic idea. The basic idea is to count something, you can kind of count them all separately and then kind of start subtracting things that you counted too many times. Okay. Cool. So maybe let me just go back and say, all right, so we've seen intersection and union, and if you look at their definitions, they seem very related. I think I mentioned this, right? The only difference between their definitions is this symbol, right? So intersection corresponds to and union corresponds to or. And that really is, so it's kind of like, let's put it up here. So intersection is like and for sets. And union is like or for sets. Right? And you can think about, so the fact that the symbols go the same way, right, that helps you remember which is which. Because you'd be like, okay, wait, I know which symbol means and so, well, and means it has to be in both sets, so that's intersection. Okay, so that's the symbol that goes with it. You can also think like the symbol for union, right, looks like a U, so that helps also. That's a nice, and honestly, I don't know, it would be a curious, I'm curious now, sort of the history of these notations. Like, which kind of came first? It could have been that someone picked the symbol U for union because it looked like a U, and then kind of went from there. Or it could be that that was kind of a nice coincidence, and they picked it for some other reason, but I don't know. So yeah, mathematical notation doesn't always make sense. Sometimes, like, there's just kind of weird historical reasons why we use a specific notation, and it's not necessarily the best notation. This is one of those happy times where the mathematical notation we have is great. Like, and or are dual to each other, and we use symbols that are upside down for each other. That like beautifully helps us remember the relationship between them. Intersection and union, we also use these symbols. They're dual to each other. They correspond to and or. Like everything kind of works out nicely. So the notation helps you remember what's going on. So sadly, that's like one of the few times I think we're going to see in this class where we actually have nice notation. Most of the time in math, it's just like, well, this guy used this notation in a paper he wrote in like 1741, and so that's what we use now. And it's like, okay, great. All right. So next page. So this is set difference. The difference of two sets A and B consists of elements in A, but not in B. Okay? And we write it like, sometimes you'll see, well, we write it like this. It's like a backslash. You might think since it's difference, you would use a minus sign. And sometimes people do use a minus sign. And often I like to use a minus sign, but as we'll see in Disco, you have to use this sign when we talk about how to do this in Disco. Because minus is subtraction. So for various technical reasons, it would be complicated to have it also work for six. So, x such that x is an element of A, and x is not an element of B. Okay, so a Venn diagram looks like this. So here's A, here's B, A minus B, or the difference in B, is this part. Okay, so it's kind of like B came along and took a bite out of A. It's like, these belong to me, you can't have them. Any questions about that so far? Okay, well, I wanted to find one more operation, and then I'll switch and we'll see how to do some of this in Disco. We could do some examples of difference, but hopefully we can make up for examples. This one is interesting. The idea of set complement. So the basic idea is I want to have like a, just like union and intersection correspond to or and. I'd like to have something for sets that kind of corresponds to not. So I want to say, like, all the things that aren't in this set. Okay, but we have to be careful, because what exactly does that mean? Like, if I have the set 1, 2, 3, what is the set of things that's not in the set 1, 2, 3? I mean, I guess it has the number 4 in it, but does that set also contain, like, Beethoven? Or, like, Next Thursday? Or, my little daughter? It's like, what does it mean, like, all the stuff that's not in there? Because, what am I allowed to use, right? So, to talk about complement, we have to already have in mind, like, some kind of universe, like, or a domain that we're talking about. And then the complement is, like, everything in the domain that's not in this set. Okay, so you have to kind of, like, restrict what you're talking about first for that to make sense. So, given a domain or universal set U, right? Or it's often called the domain of discourse. You might hear that term. I'm not going to use that term, but just you might hear it. The complement of a set A is everything in U, but not A. And this actually is very similar to difference, right? So really the complement of A is like the difference of U, the universe, minus A. I write it like this: A with a bar over it, which is really U difference of all the X, which is X is in U, but X is not in. So why do we have a notation for this complement instead of just talking about difference with the? It's just because sometimes if we have fixed a universe, then it's convenient to just be able to talk about complement everywhere and not have to always write universe minus this, universe minus that. It just kind of depends on what. So I will say, I don't want to spend a lot of time talking about this. But I will just note, set operations satisfy a bunch of laws which are exactly analogous to the laws that we already learned. So are exactly analogous to the laws for propositional logic. So basically, if you take any law that we had in terms of and, or, and not, and you just replace those with intersection, union, and complement, it's gonna be the same thing. Because, like, intersection, union, and complement are directly defined in terms of and or not. So if you kind of expand out the definitions, you're eventually gonna come down to, you know, a set defined in terms of some proposition, and then you can apply the law to that proposition, and then say, well, that was the set that, maybe I'll do an example later, but so I'll just say some examples. So for example, you know, like, A union A is equal to A, just like, or is idempotent, right? A union B intersects C, right? We know that or distributes over and, so union and intersection are distributive as well. So like this is, for example, A union B intersect A union C. And it's kind of a nice exercise to draw this out as a Venn diagram and convince yourself, you know, that this is true. You can either like kind of expand out the definitions in terms of or and see that it's true that way, or you could draw a Venn diagram and convince yourself that way as well. Some other things like, you know, we have De Morgan's laws, so like A union B complement is A complement intersect B complement. Right, just like not distributes over, in this case, or. Same thing happens here. The complement distributes over union or intersection, but it flips the union or intersection to the other one. I don't know, maybe this one I'll draw a Venn diagram just to show, right? So like if I have, so here's my universe U, and here's A, and here's B. So A union B complement, well, A union B is everything inside here. The complement would be everything outside, right? So that's this. Now what does A complement intersect B complement look like? Well, A complement would look like this. A complement is everything that's outside of A, but that includes like this stuff here, that's in B, right? B complement would be everything that's outside of B, and when I intersect them, right, I only get all this stuff out here that's outside of both, because that's the only part that would be in both A complement and B complement. Anyway, just an example to kind of show that you can also use Venn diagrams to convince yourself of these things. But anyway, but yeah, honestly, these three things right here, these are really the most important ones. I guess are there any others that are corresponding? I mean, I don't know. I think these are the three most important ones. The union and intersection are idempotent. They distribute over each other, and we have something like De Morgan's law. If you just know those three, then you'll be able to manipulate set expressions pretty easily. Right? All right. So in the last, well, let me stop and say, are there any questions before we move on to looking at how we do this stuff in this way? See that? All right. All right, so, well, not really, I guess there's not that much to say, but, so Disco can of course do these operations, so like, let me see here, let's make, well, while we're at it, I'll show you how to make variables at the Disco prompt. So you can make your own .disco file, and you can define variables in there. You can also define things right here at the prompt. The thing is, though, that you always have to say what the type of the variables are that you want to make. So I can't just say, A equals 1, 2, 3. It's going to yell at me that, say it says, that you have to have a type signature with that, and go read that at home. Okay, I'll say, okay, A is going to be a set of, N represents natural numbers. All right, and then I can say A is equal to 1, 2, 4, 7, 10. Okay, and then I'm going to also make B as a set of natural numbers. B is 1, 3, 4, 8. Okay, so now I can just use A and B to represent those sets. I don't have to type them in every time. Right, so I can just say A. Okay, so the way you do a intersection, there's a couple ways. I can just type intersect B like this, and that gives me their intersection. If you want to copy paste the little Unicode like intersection symbol in, you can do that. I don't know if I can. There's a good way to type it. No, I really don't. I guess I could here. Unicode set intersection. There it is. Unicode character. Copy. You don't have to do this, but it's kind of fun. So if you want to, this is what I do. Honestly, you just Google it and you copy paste the symbol. Probably, depending on what editor you're using, maybe your editor has some fancy way to enter Unicode symbols, but let's see. Of course, I can do union, so a union B, all that stuff. I can do difference with a backslash, right? So this is subtract from A. Just get 2, 7, 10. There was something else I was going to say. Right. So complement. So Disco does not support. It does not have a way to do complement. Anyone have a guess why? And it's not because I haven't gotten around to it. Which, by the way, speaking of not having gotten around to something, I think last time I talked about Cartesian product, and I was like, oh, this doesn't have this yet. Well, I added it over the weekend. So we can do you write it like this, greater than, less than, it looks like a little time symbol. Grace, what do you think? Why does Disco have complement?
Well, because the complement is a set up like a universe.
Yeah.
You have to set up somewhere, like, how would you, so it would have a hard time pronouncing the universe and then giving everything that's in the universe.
Right. Yeah, so Disco actually does know what universe we're talking about. We have to, basically, that's what this is. We have to say what universe we're working in when we give the type of the set. We have to say, oh, this is a set of natural numbers. That natural numbers, that is my universe, right? Say, I'm working within natural numbers, and then I'm going to pick some of those to be in my set. So Disco, it's not that it would be hard to tell Disco what the universe is, but what would be difficult about finding all the things that are not in a set? So here's a set A. What is the complement of A? If my universe is all the natural numbers. Exactly. Right. That's the problem. The complement is, 0, 3, 5, 6, 8, 9, 11, 12, 13, 14, 15, 16. It's infinite, right? And Disco can't represent infinite sets because, you could imagine a system that does support infinite sets in some ways, but it would be much more complicated. It wouldn't just be able to list the elements. It would have to somehow have a way of knowing, like, oh, this is the set which you get by taking the complement of blah, but it could like actually list the elements. And so disco sets are not that sophisticated. Might be cool, but anyway, yeah, there's no complement because it might be infinite, or in most cases it would be infinite. If I had like, I guess if I had a set of booleans or something, and it was like a set containing true, you could take the complement, it's like, oh, it's a set containing false. It doesn't have that. Yeah, so, right, and the other thing I wanted to show, or I think maybe we mentioned this, but I want to remind you of it because it may be helpful for you as as we do more disco stuff. So on the module that's out, right, there's some disco things you have to do with sets. This dot command is your friend. So many things that you might encounter in disco or you might want to use, you can ask about them with the doc command, and they'll tell you something about them. So, like for example, if I ask for like, oh, how does union work again? I can say doc union. Actually, this is a bad example because apparently I haven't actually written some documentation, but at least it shows you the type. And it's saying something about bags. It also works for sets. It kind of had to pick one, and it happened to pick bag. But so yeah, you can also use this. So this is another way. If you want to use the Unicode symbol, you can just ask Disco for documentation, and it'll tell you what the alternative ways to write it are, and then you can copy paste from that. Don't worry about this. This is basically telling you like, when do you have to put parentheses, or like. Let me do a different example that might be very. I don't know, maybe plus. So it gives you that information. It also has a little short description here, and it also has a link to, some documentation on the website. So maybe this is a good example because if there's something you want to know about and you type in doc and you don't get much information back, or it says, oh, there's no documentation for that, or there's not what you wanted to know, tell me and I'll add it, because it's just like there's a lot of stuff to write documentation for. I just haven't done them all. But if you specifically try to look up something that's not there, that's good. That's helpful information for me. It's like, oh, I should write that thing because you actually wanted it. Yeah, I actually didn't realize I hadn't done it for using, but I will do that. But in general, if I could say, I'm like, oh, how do sets work in this? I say, ask for documentation of set. It says the type of finite sets, and I can go, there's a lot of stuff here about sets. There's stuff about union, intersection size, power sets, right, all that stuff. Set comprehensions, which is like that notation where you say like, x such that x is blah, blah, blah. We talked about that last time. When you do that on the module, if you forget how that works, you can go look at some examples here on the website. All right. Any questions? Okay. I will see you all